Hi guys. This is a topic that's maybe a bit unusual for OffensiveCon, I think, because past topics were typically about reverse engineering, about memory corruption attacks. Both are things I also did back in the 90s, but I moved on mostly. And this is a topic I also worked on since the 90s, but never gave a talk on. In a sense, this is new for me, but of course, a very familiar topic as well. And I previously gave talks on the defensive aspect of it, on password security. So this is an offensive counterpart or translation. Passwords, they still remain important, and despite what others say, I think they are not going away. They will be around for a very, very long time. I don't know, maybe as long as humanity exists, or maybe not, but nevertheless, definitely not going away in the near future, maybe probably not in our lifetimes. That's because there is no replacement for them as a unique authentication factor. There are various replacements, but they are more useful as additions than as replacements. Besides authentication, passwords are also used for protecting data, encrypting it. There is no equivalent. You can have some token instead, but the threat model is very different, and sometimes you need to choose something you know. Cracking passwords is needed for lots of reasons. This includes obviously security tests and penetration tests, but also recovery of access to something where access has been lost. It's usually something you have locally, like a lost password to an encrypted file or so on. Then there are many related use cases which are not even necessarily about passwords. There are sometimes other tiny tokens of data that are hashed, and similar approaches can be used to recover these so-called pre-images. In this talk, I am going to focus on offline password cracking, which is something I spent most time on within this field of password security. There exist other related topics which will be covered to various extent. Of course, whenever possible, in a real attack, a password could be just bypassed, but not the topic of this talk. Nevertheless, important to have in mind to think outside the box and not necessarily go after the hardest way of actually trying those passwords and cracking it. Then there are various targets. By targets, I mean something that you run a password cracking attack against. This is usually, for the topic of this talk, something you have a copy of offline. So it's a hash or an encrypted file usually, or multiple hashes or encrypted files, sometimes millions of them, which is actually pretty efficient to do because it amortizes cost. An interesting thing is how projects such as John the Ripper and a bit later Hashcat approached importing those non-hashes, as we call them. We introduced, in part because this was afterthought, we started with hashes and then we added those other things a bit later. So we introduced tools that convert those non-hashes to something that looks like a hash to those tools. And another project is BTC Recover, which targets cryptocurrency wallets. They use a similar approach, I don't know, inspired by ours and independently. And one of the goals with usage of such conversion tools, this was also an afterthought for us. Initially, we just needed something that would produce something that our existing tool John would accept. But when we did that, we realized this is also a security layer, which allows, for example, to give this extracted pseudo hash, I would say, to a service provider who would perform the password cracking attack, and even after retrieving the correct password, would not necessarily be able to encrypt the data. This pseudo hash might not have the full encrypted data, just whatever is necessary to run the attack against a given target. For example, with block ciphers, there is this CBC mode, which needs basically just last two data blocks for the attack, when you can check the padding or whatever is seen after the end of encryption, of decryption of the last block. That's because there is no dependency on data in the previous blocks for correct decryption of the last block. So we do things like that. Not always possible, unfortunately, but in some cases it is, and we try. Then what we have here is basically a task of optimization. We're optimizing for speed, or actually relative speed relative to cost, relative to other goals. There are conflicting goals here. And we also optimize for focus, what I call focus. This means searching passwords in an optimal order. Again, there are conflicting goals here. For example, because when you introduce parallel processing, or especially distributed processing, you actually hurt the optimality of order. You cannot test 1 million of passwords and in parallel, and at the same time prioritize the first over 900s or 900,000s. It just doesn't work that way. So there is a trade-off here. A bit of historic background on password authentication. It started, as far as I could find, and in a sense similar to what we have today. In the 1960s, there was plain text password storage, and the comparison obviously wasn't timing safe, which resulted in issues. Obviously, plain text storage is insecure in many ways. Those plain text passwords can leak. Then there is the introduction of password hashing with multics in 1970s. Obviously, the hashes in use at the time were also weak. Similar was on early versions of Unix. But they quickly, in the middle of 1970s, realized that things were not right, that password testing was actually too quick, unnecessarily too quick. So they started to improve things. Here we see how it was initially before those improvements. And here the improvements are. They introduced salting. They actually described password policy check. It's right in the 1978 paper. It's all in there. And that the hash function should be slow. It's also in there. They introduced a fixed number of iterations, 25. And then there wasn't much improvement until the 90s, when the hash function was made tunably slow, so you could increase the number of iterations. And finally, we're starting with Colin Percival's paper in 2009 about script. The concept of memory hardness, or using a lot of memory for hashing, was introduced. So basically the task became two-dimensional. Not only computation, but also memory is needed. And specifically with specialized hardware attacks, this is very important. There exist other authentication methods, mostly starting with since the 90s. What I have found is that usually they also use passwords somewhere, or if they don't, then they are basically weaker because they do not have this authentication factor, which I have mentioned is unique. Even with those other methods, password cracking is relevant. This doesn't mean they are just as weak as simple password authentication. Some of them are much stronger. For example, I fully recommend usage of SSH key pairs. But the password cracking attack is merely shifted elsewhere, like with SSH on the client system. Now this is a section of my talk about focusing on password hashing speed. This started, at least publicly, in 1980s. Privately, I have already mentioned that the developers of Unix understood in the 70s. An optimized way to attack hashes is something like this. You go after each hash and then after each password, and you compute the hashes, compare, and that's it. They may be assault or maybe not. When there isn't assault, you can optimize it. You can optimize it, but by amortizing the cost of hashing, you reuse the computed hashes to compare against all of the loaded hashes at once. You do not have a loop, this loop outside of the hash function invocation. Then when there are salts, you optimize it slightly differently. You group by salt, and for the same salts, you do this comparison against multiple hashes with the salt, if there are, when there shouldn't be, but in practice often there are. So this is what you get. And you can optimize it even further. Which was done, something like this was done in John the Ripper in late 90s. So you compute multiple hashes at once, and you may have multiple hashes for the salt, if applicable, loaded at once. So we have a many-to-many comparison, essentially, and this construction can sometimes be optimized. And the hashing function can also be optimized. You move things out of the loop, basically. So again, you have amortization of this cost, you reuse results or intermediate results. Here is an illustration about this many-to-many hash comparison, how it can be done approximately. I first did something like this in '97 in a very early version of John the Ripper. It provided, as I recall, something like 10% speed up when running against 300,000 Unix descript hashes. So basically, about 100 comparisons per computed hash needed to be performed because the salt count is 4096. And those 100 comparisons were done sequentially, like other crackers did before. They cost roughly 10% of hash computation, which is avoided this way. Those data structures evolved over time, and they differ between implementations even within one cracker, such as within John the Ripper. Some computed on host CPU, some on GPU, and tailored to specific hash type, or sometimes are this way for historical reasons. For example, if a contributor implemented something in a specific way, we have perfect hash tables on GPU, for example, because the contributor was interested in doing that. Then there are many ways actually to reduce cost. I am framing this entire problem, as you have noticed, as that of amortization of those costs. So you reuse what has cost you for multiple purposes. And this reuse goes beyond only computations. There is also memory, space complexity in more formal terms. And when you look at real hardware, you can amortize even things such as power supply units, RIC units that your servers consume, or so on. when you have, for example, just one CPU per server, you are wasting space, basically. You're wasting the chassis, the power supplies, and when you put many GPUs, like 8 plus in the chassis, you reduce the fraction of its costs that goes per GPU. Password cracking on GPUs was pioneered by Andrei Belenko at Elcomsoft. Elcomsoft produced various shareware or plain commercial programs for password recovery for end users and for law enforcement, for any users actually. Those programs were specialized, mostly specialized to given targets, so mostly beyond topic of this talk, but they do get a mention here. Speeds were not very great at first, at least by modern standards. In fact, even PlayStation 3 reached similar speeds with specialized CPU and not a GPU. But the speeds quickly improved to tens of billions already by 2010 on multi-GPU machines. And by now they improved further, but as you can see, this improvement is still like within an order of magnitude in 10 years. Well, a bit more because it's 8 GPUs versus 1, so within 2 orders of magnitude. It's a very significant improvement, but nevertheless. Then there is parallel processing. When you compute hashes defensively, your potential of parallel processing is limited. That's because there is limited internal parallelism inside the hash function and a limited number of passwords, for example, of users that are authenticating against the server this second. For example, 1,000 users are authenticating and a factor of internal parallelism is 10, and you're limited to 10,000 hashes, 10,000 components of hash computations that you can do this second. With password cracking, it's kind of unlimited. You can be testing many more candidate passwords in parallel. But there are various other constraints, and as I have mentioned, there is the aspect of memory, more about it on further slides, and this aspect of amortization again. And there was this thing, time memory trade-off. Of course, it still exists in various forms, but what mostly doesn't exist anymore is not in use actually anymore, is rainbow tables. There was kind of fashion for them, and they performed pretty well, but applications where they're still beneficial are very limited. It will have to be something without salts or with very few different salts, or where you can predict salts, and something that actually takes a while to compute directly, so that pre-computation would be worthwhile. So the original application for Windows password hashes, for example, is no longer that relevant. What's maybe slightly more relevant is Wi-Fi, when you pre-compute for specific common SSIDs. How common they are, it's a separate topic. And actually, they started before rainbow tables were invented, so with QCrack, but was also not very efficient. Then there are other types of time memory trade-off. Most relevant here is what we do against script, for example, where we can reduce memory needs greatly by paying more CPU time for that. Then there is this formal model for cost metrics. It comes from defensive users. For attack, things may be slightly different because the attacker doesn't always directly pay for resources. The resources may be, let's say, borrowed from somewhere. This needs to be considered, but nevertheless, when you work on defense, this is what you use. This is how we computed things with traditional hash functions that didn't deliberately or didn't happen to use much memory. You could put a lot of concurrent implementations onto your hardware and compute them in parallel and get many results in parallel and have this many-to-many comparisons that I have mentioned. Then something that I'm present for completeness and for reference from further slides, something that is rarely actually found. When you do need memory, but you can use it in parallel from all those cores, this is just shared memory. You do not need separate copies of data for each concurrent computation. This is rare with password hashing, but it is common with proof-of-work functions for cryptocurrencies, especially for Ethereum. Then another alternative is parallelizable hash function, where the internal parallelism is such that you can use small cores for computation of each one hash. Then the memory is also shared in this way. This actually does happen to some extent because modern memory hard password hash functions, they have configurable parallelism parameters. So if you set it too high, this is what you get. You allow for this kind of attack. And they also have, some of them also have excessive internal parallelism, and I mean Argon 2. More about Argon 2 later. script introduces the concept of sequential memory hardness, something that prevents those two attacks I have just mentioned. It's designed that way, so you cannot share a memory. You have to provide separate copies of data for, on this slide, it's illustrated for each core, or for whatever number of cores the built-in parallelism of one hash computation has, like we saw on the previous slide. And then there is weird concept I introduced over 10 years ago, actually. There are deployments of this thing. It's not theoretical. It's currently protecting many millions of accounts, could be up to 1 billion even. We do not see those hashes in leaks yet. I guess because companies that deploy this kind of stuff, they're also careful about other aspects. So I guess there is correlation that weaker hashes are actually more likely to leak. So we can use a lot of memory if it's shareable. But obviously, if it's shareable, it also allows for parallelism in attack, so you do not have to provide separate copies of this large, what I call ROM, read-only memory here. And this is compensated for by also requiring pieces of read-write memory used in a sequential memory hard fashion, and requiring access ports for both this read-write memory and for the read-only memory. So when you try to parallelize it a lot, eventually your problem becomes having those access ports and their bandwidth, which is why I call this ROM port hard. Basically, I have already mentioned proof of work and Ethereum, ETH. It's similar to what we see here, but without the memory hardness parts, without the RAMs. So you have cores, you have ports to this ROM, and it goes on. And then you bump into memory bandwidth or something like this. Here we have addition, so it's definitely not worse than classical script. We do have memory hardness and sequential memory hardness as well. And what do we mean by a core? It's some abstract concept, not necessarily a separate core, like a separate unit on the chip. It could be a pipeline stage, it could be even a single bit entry in a register on CPU if you have rotated the problem and implemented it in a way that every one bit in a register corresponds to different hash computation, something that is actually occasionally being done. And of course, most importantly, it can actually be a circuit on an FPGA or ASIC where the core is literal. But even then, it can vary because implementations are pipelined, and sometimes parallelism by pipeline stage is just as important as parallelism across hardware components. I have mentioned bit slicing. It was introduced in '97. This was a really impressive paper that I read at the time, and immediately tried to implement. And then Matthew Quinn, he went to optimize this further and publish code. And I dug up emails which we had exchanged, so I have those numbers in here. How it was improving. There were actually multiple staged improvements month by month. There were other competing teams, unfortunately too many to mention here. So a task of optimization, a challenge, quite interesting. And it's still in progress. There's pending improvement that should give a few more % of speed ups that I haven't integrated into John's repo yet. I have a copy, so that's pending. Another interesting thing is the many-to-many compare function. It's replaced with many-to-one, but computable in logarithmic complexity. So we also have that way of doing things. Let's wrap up on those techniques. A lot of different targets we have, and it's a lot of effort to optimize stuff for each platform, for each hash or each non-hash especially. We do try to do this. We do try to share whatever we can between those implementations. Stuff is open source, so we reuse what others did, and others can reuse what we did. And then there were these efforts, I mentioned a couple, to have code generated automatically from some specifications that is maybe easier to write or is more shareable across different targets. As it happened so far, those, as John Dev Kit is called that way, but it's not directly used for our development. It informed some development decisions. What optimizer found will later implemented manually anyway. And then there is OpenCL, which is also an abstraction layer. For example, it does instruction interleaving on its own, so we do not have to bother. And it's understandable. Hashcat dropped manual support for CPUs and uses them only through OpenCL these days. And then there's also runtime tuning. So when you download a password cracker and run it on your system, you do not necessarily get the best performance, unfortunately. We have auto-tuning, and Hashcat does have auto-tuning as well. But sometimes it finds suboptimal parameters. Basically, you want a password cracker to start quickly, within seconds. So what it could have probed within seconds, it does, and uses that basically for running the session. And sometimes it's possible to do better. Manual tuning. And here are some historical speeds. I already mentioned that Unix switched hash type in the 70s. So you can see the effect of the switching. It's basically performance dropped by 2 or 3 orders of magnitude when they introduced slow hash in those 25 iterations. And then speeds kept increasing. You also see the effect of bit slicing here between implementation on the Pentium and the Alpha in '98, for example, benchmarked here. It was pretty much like going from, felt like going from CPU to GPU. Basically, I had both of those machines. Well, not the same shown here, slightly different clock rates, but similar hardware. And yeah, getting things to run 20 times faster, like CPU and GPU. I omitted lots of intermediate steps. Then we had contributed, Denis Borykin implemented things on FPGA. Not the first attempt to use FPGAs for password cracking. Others did use as well. And we had projects to use FPGAs with John Turipa before, starting in 2014. But the first time it was integrated in a released general purpose password cracker with full functionality, including candidate password generation on GPU, on FPGA configurable in the usual way, and basically usable just like a normal device, like a CPU and GPU and along with the stuff. Speeds kept increasing. As you can see right now, latest GPU is about 6 times faster than latest CPU. Then for hashes that you can still use, for example, bcrypt that was introduced in late 90s, it still gives reasonable speeds today for defense and for attack. There is no such drastic increase here. Because this hash type actually just happens to use a little bit of memory. It wasn't specifically intended as a defense against GPUs back then, but it happened to do the trick. Actual speeds for hashes in use now would be lower than what you see here. It's benchmarking at a historical setting for consistency. For Windows hashes, things are not so good, obviously. They unfortunately still in use. LM hash on this slide is historical, but NTLM hashes are still in use, and speeds increased up to hundreds of billion hashes per second. Also, as you can see here, Hashcat is not always the fastest. It is usually the fastest or often the fastest, but to accept this as an absolute truth or paradigm that it's always this way would be wrong, and sometimes you do need to test other tools. They may run faster. Then I mentioned those NTLM hashes. Things for them are in a way even worse, even slightly higher speeds than for LM. But of course there is no password length limit that existed for LM hashes and made them even weaker. So anyway, 2 terahashes per second on GPUs obviously makes those hashes unsuitable for use. Unfortunately, Windows still uses this, and somehow penetration testing is still a thing when of user hash databases, password security audits and tests. I find this quite unreasonable. Well, it is reasonable to crack one hash when you need during the penetration test. When in a security audit, what do you achieve? You have cracked like over 90%, and maybe you can reduce this with really complex password policy to, I don't know, 50%, maybe 10%, but it's still a lot of passwords crackable unless you basically use generated passwords, which is actually a reasonable workaround. What else can you do? Nevertheless, at OpenWall, we do have a password policy enforcement product for Windows as well as for Unix. It's actually originated as a product for Unix, but then we ported to Windows, and we do offer this for those who somehow need to enforce a password policy, which actually makes sense against online attacks. Because in an online attack, you obviously are quite limited in the number of passwords you can test, so why not? But for the hashes, no, not really reasonable. Finally, there is Argon 2 as an example of a sequential memory hard hash. It's a pretty good one, but I did mention it may have excessive parallelism, and here we see this parallelism is used on a GPU. Here we can see 480 hashes computed in parallel, whatever amount fit in 8 gigabytes of GPU memory here. But at the same time, we are able to use 15,000 kind of cores, I mean 32-bit wide execution lanes, which NVIDIA actually calls cores. Of course, the GPU doesn't even have this many cores, so we have kind of excessive parallelism here. But as I have mentioned, pipeline stages also need to be filled, so we are computing about 5 times more instances of a parallelizable component of Argon 2 in parallel, 5 times more than the hardware has resources to compute with separate hardware resources. But of course, we need this extra parallelism to fill the pipelines. This ends up being about 4 times faster than a dual CPU system. Both are pretty old. I'm sorry, whatever I happen to have for this example. But I think it will remain similar, or maybe GPUs will actually improve further upon the CPU with newer hardware. So let's wrap up on hashing speeds. We discussed the speeds of hashing and of comparison of hashes, but mostly didn't yet touch the topic of candidate password generation and avoiding or suppressing duplicate candidate passwords generated. Even though speed of those operations is also important. But for contemporary targets, speeds haven't really changed much in tens of years. It's still on the order of 1,000 checks per second. And at these speeds, other aspects matter more than the raw hashing speed. So the primary other aspect is focusing the attack. Again, here's a historical example. In '83, a program was published, a password cracker program, that did things like this. It's actually a derived version of it, I think. You could specify right on the command line how you wanted to adjust your password guess attempts. There were several options here. They could be combined, so functionality in a way similar to modern password crackers, but rudimentary and not configurable other than from the command line. And then there was crack. It appeared in '91. Here's an example of what it achieved, as its author Alec Moffett wrote in a file attached to the documentation. So you can see diminishing returns from longer runs of it, and the need to optimize the order in which candidate passwords are tested. The latest version of Crack 5.0 had the concept of dictionary groups, again for testing more likely first. And it also mangled user-specific data, like we also saw earlier crackers do even in the 80s, but here it was configurable finally. Those were mangling rules. Here's an example rules that is actually still supported by John the Ripper and Hashcat. The same syntax still works. It was introduced by Crack. And it also existed in tools by Inside Pro, which is how Hashcat got it. Here are some extensions to those mangling rules. For example, in John the Ripper, I added the preprocess, so you did not have to edit all the rules manually, and you could specify patterns that are common to a group of rules, and a few other things. And Hashcat was first to implement those rules on device in OpenCL or CUDA. Here's an illustration of what rule sets exist and how they evolved. At first, they were written manually by Alec Moffat, then by me for John, and I think Inside Profolks also wrote most of these manually. But of course, we can use scripts, then store results. With John the Ripper preprocessors, I have mentioned, the writing task is simple, and you do not really need to pre-generate. The preprocessor would take care of this on startup. Right now we are up to millions of rules in the largest rule sets, especially as pre-process expansion. Again, we optimize them for optimal order, more likely first. So it's more likely to crack a password first. There were even contests for that. And there is this task of tuning ruler sets for optimality of order and what's included, what is not. There were many efforts to do this. I started with this in the 90s, but did not release any tools, only the results. And in 2012, Simon Maréchal tried to do this more formally and released code in Haskell that did stuff, but it was kind of abandoned and it was reborn, and maybe it's still useful. It exists on GitHub. Then maybe because of the not invented here principle, it was easier for me to do things from scratch, so I introduced the statistics feature in John the Ripper and used it to optimize our default rule set just 2 years ago. Here the results I achieved. The first 40% or 3,000 of rules crack 40% of what the entire rule set cracks, and crack 97% of what the entire rule set cracks, and the rest cracks the remaining 3%. Then there is this topic of targeting. I already mentioned using user information for generating candidate passwords. And when you do that, you need to focus on the right hashes. You do not need to waste time, not exactly waste, but to use time less efficiently when probing those passwords against other users, except for the same salt when it's almost free. So there are different implementations here, and Hashcat got similar functionality recently as well. There is a problem of duplicate candidate passwords. They result from having similar input passwords in the input word list, especially if it's a common password list. Then you apply mangling and you end up with likely passwords, but some of them could be repeats. There is a way to try and avoid producing those duplicate passwords. The rule sets themselves can be adjusted to reject input words that the rule set designer knows that would be duplicate with what some other rule in the set produces. John the Ripper extensively uses those flags most of them came from crack, but Hashcat rule sets typically don't use those reject flags, so there is a high percentage of duplicates when you use Hashcat rule sets, including when you use them with John the Ripper, obviously, except that we have this duplicate candidate password suppressor, which is quite efficient. Here we use it at very little memory, 256 megabytes only by modern standards. It's nothing. Nevertheless, this is the current defaults because I realize people sometimes run John in a VM and they may have little memory and they would complain if it refuses to run, so the default is slow. And even the slow default removes half of the duplicates in a 50 gigabyte stream. So a suppressor that is 200 times smaller than the produced output is half efficient, reduces duplicates in half for both John to Reaper and Hashcat rule sets. This slide talks more about this, and Hashcat actually introduced its own suppressor first in 2018. In John the Reaper, it's only 2 years ago in 2022. But Hashcat is very different. It's a client-server architecture, which is on one hand very useful because you can suppress duplicates across multiple jobs, concurrent or subsequent, but nevertheless. On the other hand, it's harder to set up a little bit, but at least it's not a default in John the Reaper. The suppressor is enabled by default, as I have mentioned, when needed. And this client-server thing, it's also slower, not so much because it's client-server, but I think mostly because it writes to disk and not only to memory. And I guess this is basically, I didn't really look, but I guess this is IOPS capacity of an SSD, 50K per second, something like this. This is how the suppressor in John the Reaper works. I use a data structure similar to a cuckoo filter, but a degraded one, which isn't cuckoo anymore. I don't know if it has a name. I tried to look it up. I couldn't find. It's so trivial that I suppose someone who should have done it before, and it should have a name. I couldn't find. Maybe someone knows and will tell me. So basically, we fill this table, and when it fills up, we throw something away. And each line is, each bucket or line in this illustration is filled independently. So once we have filled 8 fingerprints with the same hash index, and we have another fingerprint to add to the same bucket, we throw something away, evict it, and I experimented with this stuff of different eviction policies, like general for caches. And it turned out that it's slightly more effective to evict only from the second half of each row. So this is the default, it's configurable. The first half may be locked. Basically, you are checking for duplicates against recently produced candidates and against those produced at the start of your job. But you drop the middle. And this happened to work best in most of my experiments. Then there are deduplication tools that are standalone or unique, integrated in John the Reaper. I wrote it in '98, which can fully remove duplicates, not opportunistically like the suppressor I have just mentioned, but fully and predictably. They vary in their properties, multi-threading and so on. Unique wasn't multi-threaded. Then there are multi-threaded implementations now, which unfortunately sometimes introduces some unpredictability of order when there are equivalent solutions. Then where do the word lists come from? Historically, they were literally a list of dictionary words. They were also tiny lists of common passwords, but they were just a few hundred or a few thousand lines at most. Things started to change with the RockU leak, which somehow was accepted by the community. At first, folks were cautious to redistribute it, basically someone else's leaked data. But nothing happened, and folks became brave, and now it's the gold standard for all of this stuff, for security researchers, for academic researchers, and for actual use in security audits, penetration testing, and so on. And then, of course, there are larger password lists leaked, breached, from which common password lists can be compiled. There were a number of forums where people exchanged, like for hobby or for whatever reasons, uploaded hashes, uploaded what they could crack, others cracked more, also uploaded, and so for weak hashes, at least for unsalted fast hashes, 90% plus were typically cracked, sometimes reaching 99% even. And those files were also retrieved by defensive researchers and users, including, for example, for Have I Been Pwned, which is a defensive project service which allows to check for breached passwords by the users themselves or by organizations that allow a password to be used. And those sites are unfortunately not available anymore, but content, at least for hashes.org, mostly can still be found and used, and can be used to recrack those password hashes from Have I Been Pwned. I also mentioned we have a product for password security enforcement. It's PasswordAQC. It's integrated in Rocky Linux, which is a project I'm also now contributing to. For example, working on the security special interest group providing replacement glibc, OpenSSH packages that are different from Red Hat's security hardened. And we also package PasswordAQC in there, which allows to enforce password policy. And one of its recent features is it can perform an offline check against the Have I Been Pwned database. It uses a cuckoo filter for that. And the current Have I Been Pwned consisting of approximately 150 million unique passwords is compressed to 3.5 gigabytes. So if you have some important server, of course, you can now afford those 3 gigabytes and also satisfy compliance requirements, for example, that exist in the US from NIST to check new passwords against publicly available breached passwords and disallow those. And as I had already mentioned, this also works on Windows. We have a port for Windows. About those input databases that haven't been pwned, Rockio, I have used both to optimize John the Ripper default word list. I used an approach that produces a list that is both effective and obviously ethical to redistribute. As I have already mentioned, people seem to have no problem redistributing Rockio as a whole, but I chose to play it safe, and am redistributing in John the Ripper only a subset of Rockio that overlaps with what's seen in other breaches to have greater assurance that these passwords are not a person's unique password and that they actually used across different users, across different sites, which is also great for efficiency. Then there is this topic of probabilistic candidate password generators. This is something I introduced in 95 and publicly released in 96 in the first version of John the Ripper. In hindsight, it can be called a zeroth order Markov chain. It's a degraded chain, not really a chain, but basically just probabilities of characters are used individually for each position, and we have individual character sets for each position optionally. Then later same year, things progressed to actual Markov chains or similar structures like second order Markov chains where each character depends on two preceding characters and probabilities are considered. This was first proven to be more effective by another person, the sorcerer, who released this star cracker basically a program that existed very briefly only for DOS, but it did prove a point, so I give him credit. And then another feature I introduced, I guess, was first to introduce it, is training of probabilistic generator based on previously corrected passwords as a standard feature for password cracker. So once you have cracked enough, you would retrain it. And I also improved this generator to consider more inputs, which were later proved useful for parallel and distributed processing. One unique property, by the way, of this so-called incremental mode is that it can search the space exhaustively in an optimized order, but exhaustively. This is still rare today among competing implementations, competing solutions. Second, there was this recurrent idea about vowel consonant patterns. It keeps coming up. It kind of was obsoleted when we went with real Markov chains. And there is this external mode thing in John the Reaper where I implemented a specialized language, actually almost like C, and we implemented many things in it. So it's configurability without having to rebuild the entire program. And there is this thing as mask mode. It was introduced in Inside Pro, then used in Hashcat, and finally we got it in John the Reaper as well. It allows to specify a pattern, for example, for a forgotten password, or to optimize the search order by having multiple patterns that you test in optimized order. And it's also very useful as an accelerator when you have a much faster device that computes hashes faster, but you generate complex passwords on host or with complicated algorithms. You add mask mode on top of it, and you have hybrid modes that have mask on device and something else probably on host. And we even support this, for example, with FPGAs, as I have mentioned. Then there were academic advances in identifying passwords through Markov chains, in this case, the hidden Markov model. And I mention this here in part because it's first mention of extending the Viterbi algorithm for password cracking. Code wasn't released, unfortunately. Then the similar stuff was actually implemented in 2005. Again, I don't know if code was released, but it was actually implemented by Simon Maréchal, contributed to John the Reaper, and became Markov mode that we have. This is first order Markov chain, or in other words, it considers only one preceding character, so groups of 2 characters. It outperforms incremental, what I had implemented in some tests, but requires advanced configuration of job size, which is inconvenient. And then there was further academic research. Unfortunately, those two components are still not integrated in any generic password cracker that I know, not in John the Reaper, not in Hashcat. They exist as standalone tools and actually maintained, so you can use. But it would be great to actually integrate them. One is usage of probabilistic context-free grammars, and the other is further extension of the Markov chains concept. And actually, the latest implementation of PCFG by Matt Ware, it integrates Omen as well. So there's a hybrid. And then about passphrases. Things are not so great here. but some implementations appeared, like trivial per scripts that I posted to a mailing list back then, and then Hashcat got its combinator mode, and then its Prince processor, which then was contributed to John Zurip. I'm very grateful to Tom for offering that. And there are specialized mangling rules and processing of publicly available data like books from Project Gutenberg, which is something I did but never released. I probably should. And then there is the topic of doing this probabilistically also for passphrases. PCFG does something like this. And then I learned of this phrase, rephrase. Just yesterday, someone started this discussions and just uses mailing lists, so I added to the slides. And there is an idea I have, kind of middle ground, not going after whole words, but maybe after syllables or any substrings, and to reuse existing models that are intended for individual characters. We can do translation to indices and back. And translation back, by the way, is easily implemented through John Zurip external mode, so you do not have to run a separate program for it. So one of those ideas for the future. And then there are neural networks. There are various achievements recently, starting in 2016. The first one is actually produces a pretty good stream of candidates without any duplicates and with low memory needs, but it's kind of slow. And whether it's unacceptably slow obviously depends on how slow your hash is or non-hash is. So if you can use it to full capacity, your hash computing resources and the slowness of this doesn't matter if you do it asynchronously. And then there are generative networks that unfortunately produce duplicates. I have included references to some papers, sorry for not citing them properly. Many have like 5 authors or so. There is one I singled out as looking best, in part because the others did such a thorough job of comparing it against other competing solutions that are actually serious competitors. And then you obviously do not use candidate password generators each on its own. You use them in combination. You can run them in parallel several jobs or sequentially, but anyway, what matters is the overlap of candidates they generate, so those duplicates, and what matters even more is the unique password they generate, the lack of overlap between them. And of course, you ideally would also suppress duplicates between the different generators, but not necessarily. Workflow is very important. We see it, for example, publicly see it in password cracking contests, which I highly recommend. CoreLogic started doing those in 2010, and they occur every year. Sometimes there is a second contest the same year from some other organizers. It shows how different tools, different teams, different strategies actually perform versus each other, and then teams publish write-ups, which I highly recommend to read. So just look this up, correct me if you can, write-ups, and there you have descriptions of good password cracking workflows. My thoughts about the future. Again, I split this into speed and focus mostly, but also features. Obviously, existing kinds of computing devices will keep becoming faster, and cache and speeds will increase. This will be counterbalanced by increases in tunable settings of hashes or KDFs used defensively. We will tune them to also use more iterations, more memory. So hopefully it will still remain about 1,000 per second for attack on similarly priced hardware for targets that are tuned recently and use up-to-date algorithms. Then I have this idea about ASICs and open hardware FPGAs. I think it's high time we have open hardware FPGAs, and this will happen. We already have tiny ones, but I wish large ones would become available as well. One idea I have is to use a tiled design so that you could reuse the same bit stream for different sizes of FPGAs, something that doesn't exist for commercial FPGAs currently. Basically, if an FPGA is proportionally larger, like upgraded from 10 to 20 tiles, then you just load the same bit stream that occupies more tiles, and you have more cores running in parallel. For example, each tile can run, I don't know, 100 cores. And about ASICs, one idea I have is how it could be funded. There are a lot of lost cryptocurrency wallet passwords right now. And if there is a way to speed things up by a factor of maybe 100, which is realistic, I think some who haven't lost all of their savings could put some $1 million into ASIC development. Actually, prices for custom ASICs start way below this mark now, in part also due to cryptocurrencies. Many startups appeared that did ASICs on a small scale. And then such ASICs, I guess, could also include on the same die other hardware, including maybe even open hardware FPGA, and maybe some components in that ASIC could be reusable. For example, SHA-512 cores could be reusable both as a specialized ASIC for Bitcoin wallet recovery, looping this SHA-256, SHA-512 in the way that Bitcoin Wallet's KDF does, and also available for use from FPGA as hard cores, it's called. So I think there is real business potential, community potential here, lots of things. I do not see anything blocking this from happening. Of course, there are also minor optimizations planned. For example, bit slicing, which is actually rarely applicable. Currently, it's used for algorithms that are based on DES, but it's also applicable, happens to be for Lotus Domino hashes. They use as boxes that are larger than DES, but not too large for bit slicing. So I already have this in a pipeline. The same person who contributed the new DES's boxes to be integrated. Also, on my suggestion, implemented for Lotus Domino, so also to integrate. For focusing the attacks, I suggest better password support, better passphrase support as a primary focus for implementation and for research and design of new algorithms, and also for compiling and releasing data sets, like I mentioned, the Project Gutenberg books, extracts that I already have need to package up properly and release. Then there is the idea of arbitrary tokenization, similar to transformers, actually. For neural networks, there is this duplicates problem with generative ones. I hope someone finds a solution, if not a complete solution, then at least ways to make them generate fewer duplicates. When it's about 50% at 1 billion, who knows how many it would be at 10 billion? Would it be 90%, for example? I worry. These things tend to be that way. And I would also suggest releasing pre-generated and pre-filtered output without duplicates. It's some gigabytes, but by modern standards, it can be hosted and downloaded, no problem. Also, I think neural networks can be applied for targeting specific users, including in password recovery cases, for example, when providing a service to someone with a lost password to encrypted data. You know their name, you know their website, and no reason to do things manually or to crawl with just algorithmic scripts, and you could also use neural network training and produce candidates. Of course, again, obvious further development is support for more non-hash types or hash types as well, obviously. Then support for script ROM. As I mentioned, those hashes didn't leak yet, but I guess it would make sense to be able to audit them in case the organization's password policy enforcement somehow failed. They need a way to be able to find out. And a related topic is the usage of unified memory on GPUs when you need to exceed the memory size of each individual GPU to use the memory across all GPUs, or a GPU plus host memory, of course with lower bandwidth, but nevertheless probably not as much slower as you would run with the time memory trade-off if it's applicable at all. Distributed processing is currently implemented. It's lacking. I don't like what we have, really don't like. For example, in Johnson Reaper, we do have MPI support, which runs well across homogeneous clusters. But when you try to run it across different systems over the internet, it's not so good in many ways, including efficiency and including even security. There's also idea for ease of use. Again, with end-user password recovery use cases and providing the service, a lot of time by the service provider is wasted to talk to the user, to get the information out of them, and to script those attacks. All of this could be automated, especially now that LLMs exist, and UIs can be arranged with question trees like in various surveys is done. It can also be done to inquire the user about important aspects of their forgotten password, whatever they can recall, and then the attack can be implemented automatically. The takeaways are that the topic is simple on the surface and has low barrier to entry, and it's easy to progress from there, so it's very welcoming. But it also has opportunity to do serious computer science engineering, to consider non-trivial social aspects, and to compete with lots of others. In many cases, for example, in contests, you can win or you can lose. With cryptocurrency, you can be rich or you can be poor. And there are many other reasons to have efficiency. Obviously, also when you are protecting systems and you want to identify all weak passwords, of course, you can identify all, but at least most, and to do it no worse than the attacker will. And this also informs decisions for defenses. For example, I wouldn't have designed scripts the way I did if I didn't work on Johnson Reaper before. So this is closely related as most other offensive security work that you guys are doing. And this stuff needs to be available publicly also to level the playing field. Finally, I'd like to credit CIQ, a company I recently joined, which supports development of Rocky Linux. And even though we do not do offensive security at CIQ, we do open source and defensive security. They encouraged me to give this talk, so I'm grateful to them for encouraging me to spend time on this off-topic talk.